Welcome back. This week, we discuss about the root locus. So again, we are providing class online. So please work on the homework self-correction, which will be in class today 4 to 4:20 p.m. and upload to the Gradescope. And others meeting will be Zoom. And then if you have any live questions, please post your questions on the Google Doc, or you can unmute yourself and ask questions. And if you have any other questions, please post on the Piazza. So today, we started from the homework. Then we will discuss the project, which you did a sun job for the Friday. And then we will review the P control again and the root locus concept. We may move on to the examples. And then on Wednesday, we discuss the sketching rules and then justify root locus sketching rules and how we can use these sketching rules for the P or PI control. So for the homework, so we review the homework 7.10, which asks about for the unit feedback control system. Means that there is a G and then H. So this is a feedback control system with H equals 1. So that's called unit feedback system. And it asks about the system response of this total system. So it means that we need to calculate, we need to do block diagram reduction. And the calculate G closed loop system, which using these equations. Then you find out this equation, and then you can compare this characteristic equation, which is to this characteristic equation, and then compare the coefficients such as omega n squared should be 5,000, and then 2 zeta omega n should be 75. And they can find out the damping coefficient. Then using this equation, you can find out the percent overshoot. Similarly, you can find out the settling time. Also, you can calculate the steady state error for unit step input, and then by applying the final value theorem, which means the error at infinity is the same as limit s approaches to 0 s times this. And this works again only if the system is stable. Otherwise, if there's only one pole can be located at 0 and other poles should located this left half plane. Otherwise, the final value will not exist, and then you can't apply the final value theorem. Actually, if a pole is located at right half plane, the steady state error will be infinity. So anyways, you can calculate this, or because this is a unit, there's a free integrator or type 1 system, the steady state error should be 0. Why, if there's a free integrator, makes the steady state error 0? This is because, let's say for this kind of system, as time goes, let's say the response looks like this. This is reference, then this response, and this is T. So this means that this is an error. This is an error, and then in the beginning, error will be very large. And then let's say the y-axis is error. As time goes, error approaches to 0. So what does it mean? If not the 0, even like if there's only P controller, error becomes, let's say, 0.001. And if the error is slightly larger or equal to the friction of the system can't approach to the exact reference, because the friction will against to the the balance between the input and then friction. So therefore, it will not approach to 0. If there's an integrator, then it will accumulate the error as time goes. And even if the error becomes very small, the sum of the errors still be a little bit large. Therefore, it has some force or some momentum to drive error 0. So therefore, the steady state error can approach it to 0. We'll come back this again when we discuss about the I as an integrator controller, but the integrator again sums the error and try to drive the steady state error 0. And then let's look at another homework, which was the quadruple. So this homework actually integrates everything we learned so far. So in the beginning, it asks to apply the KVL and then find out this equation. So it's very common equation. We already look at it. And then we already know that Vm, which is a back EMF, is nothing but the Km, which is back EMF coefficient, times omega, which is angular velocity. And then also we know that torque is also proportional to the current. That is motor side. And then the motor torque, which is this part, will drive the motor and then overcome the friction, and also drive the propeller. So if we arrange this equation, you will get exactly this equation. And then the propeller force will make this system float. And then also it should overcome the mg. And if you be careful about all this sign, you will get this equation. So once you arrange all these equations, then you will get this big equation. But thankfully, we can say that we can ignore the gravity. So this term conveniently disappeared, and we get this equation. The better news is that even we can approximate this system as a second order system. So we can use MATLAB to find out poles. And then it turned out that there is a two poles which is located 0. Let's say this is the imaginary axis and real axis. And then minus 1.4. Other two poles is located far, far away left, which is even -2 times 10�6, and then -2 times 10�3. So it means that this pole is really fast. So it means that we can almost ignore these two poles. So it means that this system will behave like a second order system. And because there's only one pole at 0, so therefore this system will be stable. And also, don't confuse between open loop system and then closed system. So why I'm saying this is that for the steady state error, for the closed loop system, for the GS will be approached to 0 for the step input. So it means that if there's a G, like if you're looking at the error here, the error will approach to 0 because there is a one free integrator like this, almost. But if you look at only the response of the G, because there's an integrator, it accumulates this step response. So it increases in time in more like this. So steady state response will look like this. For the open loop system. So here, this is a closed loop system. And again, if you look at the closed loop system response, because there's one free integrator, the steady state error will approach to 0. Looks like this. And of course, if you do block diagonal reduction, you can anticipate, well, if you look at the pole location, you can anticipate you can predict the peak time, which is omega d, using this will be exactly omega d, and then settling time using this 4 zeta omega n. And almost that's it for this. So again, for take-home message is that you can, using your already learned knowledge, you can derive equation of motion of this electrical and mechanical system. And then you can find out dominant pole. There are several ways to find out dominant poles. You can start from the initial equations, or you can look into the pole and then decide whether it will behave something like a second order system.